Good evening, ladies and gentlemen, dear colleagues. I will try to give you a brief presentation of the paper that I wrote with Professor Marija. It is an overview of the main concepts, characteristics, use, and energy piles design methods. So, okay. So, as you all know, there are many different types of structures that have pile foundations. And basically, pile foundations are a form of deep foundation. In general, these piles may be of different materials, such as they may have different geometric characteristics as well as building technology. We use them to provide support for the upper part of the structure through interaction with the ground or soil structure interaction. On the other hand, energy piles represent an innovative technology for the foundations of the structures, and they use geothermal soil energy to heat and cool the building in an efficient and economical way. It is basically a source of renewable energy, and it is in use for over 30 years. Ground source heat pumps, or gshp systems, provide heating and cooling of the buildings by circulation of the fluid within the system between the heat pump and heat exchange elements. When we equip building foundations with geothermal loops connected to gshp system, we can obtain an average of about 15 to 25 of the building heating and cooling requirements. The use of geothermal energy from pile foundation began in 1984 in Austria and Switzerland. Basically, the advantage of this system is that we use already required concrete piles as structural elements, so they do not need to be additionally installed like conventional thermal energy utilization systems. Okay, so today energy piles are basically used across the world. Among European countries, they are mostly used in Western Europe, in countries such as Germany, Switzerland, United Kingdom, Scandinavian countries, etc. Unlike the energy that is obtained from fossil fuels, such as coal, oil, or natural gas, geothermal energy is clean and renewable energy source that makes no contributions to the increase of CO2. Okay. So we have a difference between shallow geothermy and deep geothermy, which is represented on the picture. In general, geothermal energy can be produced from water, soils, and rocks where the temperature is around 10 to 15 degrees Celsius in average. And this is the reason why in recent years there is increase in use of shallow and deep geothermal energy. I don't know, I think most of you know this, but concrete has a good thermal conductivity and thermal storage capacity. And because of that, it makes it an ideal medium as an energy absorber. In these two images, we can see the way that that absorber pipes are incorporated in a reinforcement cage of an energy pile. So basically, the creation of an energy pile is a relatively simple process, and it includes the addition of the U-tube pipe. In this slide, you can see a typical gshp system scheme, where you can see energy piles, which are basically foundation system that is mostly reinforced concrete, and geothermal loops. In the most parts of Europe, seasonal ground temperature have a relatively constant values below the depth of approximately 10 to 15 meters. Like I already mentioned, those temperatures amount 10 to 15 degrees Celsius. And basically that makes them an ideal source for heating and cooling of the building by using energy piles and ground source heat pumps. On these images, you can see basically the seasonal soil temperature depth relation. The range of temperature changes in the ground caused by geothermal energy utilization is rather small, but that is a field that's not thoroughly investigated. Like, if we consider the use of energy piles like the problem of mechanical engineering, we can also analyze the same problem in the field of civil engineering or structural engineering. So, because of that, we cannot neglect the effects of cyclic temperature change, which can affect the pile system. So, like I already said, because of that, some countries still have not accepted this concept because of the concern of the potential impact of cyclic temperature load on the structural performance of pile. It can affect its load capacity and settlement issues. Because energy piles are different than regular or conventional piles because we have additional load, which is mechanical and thermal load. During the heating and cooling cycles, the energy pile and its surrounding soil would expand or contract depending on the load, type of the load, and in turn it will affect the structure-soil interaction. As a result of this coupled loading condition, it is necessary to thoroughly understand the effects of cyclic temperature load on mechanical behavior of soil and pile-soil interaction. So, when I was speaking about that, as you know, from the structural aspect of design of piles in general and energy piles, we have European norms and Euro codes which we use to design our structural elements, structures, etc. Design of thermal piles requires consideration above and beyond the usual pile design process. The aim of the pile design should be to quantify the thermal loads and then apply factors of safety currently used in the normal pile designs. What does that mean? Well, for example, when we design structural elements or structure as a whole, we have two limit states, ultimate limit state and serviceability limit state. We have some regular consideration when we analyze regular or conventional piles, but when it comes to energy piles, we also need to consider some other aspects, like, for example, at ULC, we need to consider the bearing capacity of the pile compared to the applied pile load, and soil properties change as a result of cyclic temperature load. So basically we need to incorporate in our calculations the cyclic temperature change. SLS considers pile settlement and structural performance at design loads, as well as thermal expansions and contraction of the pile caused by heating and cooling. So what does that mean? That means that we have certain deformations and stress changes in our piles because of the change of the temperature. So, that was previous slide. Okay, this is also the structural aspect of the design of energy piles in general, and we can see mechanisms for response of pile to thermal loading. You can see, I will just name it, so you can see mechanical load only, cooling only, combined cooling and mechanical load, etc., etc. We can conclude that there are different type of reactions of the piles, depending on the type of the load. So, one of the effects of the cooling load is shrinkage of the element, and the effect of the heating load is the expansion of the element. If we apply that for a long time with cyclic changes, with cyclic loads and changes in the temperature, it eventually can harm the element or the elements, if you want. So basically, based on the results of the analysis of the authors, which are listed here, we can see the change in axial load of energy pile, depending on if the pile is loaded only with structural load or combined load, which means structural load plus cooling or plus heating. What can we conclude from this diagram? Well, we can see that structural load plus heating of the element induces a bigger axial load, while structural load plus cooling of the element induces, how can I say it, lesser forces in the pile. Also, we cannot neglect the long-term effect of the exposure of energy pile to cyclic temperature change. It can affect its bearing capacity and settlement. Settlements of the structure may be are not neglectable because they may lead to bigger issues during the long-term exposure, because it can lead to weakening of the capacity of the structure. It can lead to damage, and essentially, if you have an earthquake with damaged structure, you can have a really big problem if it leads to the collapse or big damage on the building. As a result of changes in stress-strain relationship due to temperature load, soil-structure interaction will be affected. Because of that, better understanding of the response mechanisms is necessary. Okay. So, the use of geothermal energy have a lot of potential, and at the end of 2010, geothermal energy was directly used in 78 countries for district heating and cooling and geothermal heat pumps. GSHP have the largest energy use and installed capacity of almost 70% and almost 50% of the worldwide capacity. So, exploitation of shallow energy, geothermal energy as a source of renewable energy, and use of shallow GSHP systems can play a key role in the process of CO2 emission reduction. I should maybe mention that world leaders in installed GSHP units are the United States, China, Sweden, Norway, Germany, and some other Western European countries. You can see in these charts what I already mentioned. So this is geothermal direct application worldwide in 2010. In Europe, the countries with the highest number of geothermal heat pumps are Sweden, Germany, France, and Switzerland, which is expected because they are developed and very rich countries. On the other hand, we can see that some mid-European, East European, or Southeast European countries have a lesser use of geothermal heat pumps. In the period of 3 years, 2012, 2013, and 2014, the current number of GSHP installations in the EU reached a total amount of 1.3 million. So, I don't think that that is necessary to say something else. You can see that there is an increase in the use in the period of 3 years. This is a really interesting chart, and it is used in many papers. Essentially, it shows the cumulative, it shows the increase in use of energy piles in the United Kingdom, and also it shows the effect of the use of energy piles on the reduction of CO2, or if you like, resultant annual CO2 savings. These charts show the increasing use of energy piles in Austria since the period when they begin its use in 1984 and in the next 20 years. There are a lot of examples of implementation of energy pile-based GSHP systems, and I chose two. Basically, one of them is the example of implementation in Rosborg Gymnasium in Denmark. It was the extension of Rosborg Gymnasium, and it was founded of 200 energy piles that have supplied the healing to the living area of almost 4,000 square meters since 2011. The flaw in the design, if I can say so, was that the mechanical load, when the piles were designed, only the mechanical load from the building was taken into the account, which is a mistake, and you could saw in previous slides that it is really important to incorporate cyclic temperature load in your equation. So, anyway, at the end of the study, the authors have concluded that heating that was delivered by the GSHP system during the period of the study corresponded to 95% of the total heating requirement, which is, I think we can all agree, pretty high. So basically the results of the study indicated that that the GSHP system was a viable option. The other example, which was interesting to me, was implementation of energy pile GSHP system to the dock midfield, the Terminal E of Zurich Airport. Terminal E was founded on 440 cast-in-place concrete piles, and they are 30 meters long. Of those 440 piles, more than 300 were converted into energy piles in order to provide heating and cooling of the building. Like in the first example, they concluded that this was economical and pretty good solution. So, on this graph or chart, we can see monthly extracted and injected energies in the piles. So, that leads us to the conclusions, which I will read you now. And in order to mitigate the effects of global warming and the increasing use of fossil fuels that are contributing to the emissions of CO2 in a timely manner, it is necessary to adapt present-day and future society and technologies to the greater application of renewable energy sources such as solar, geothermal, and wind energy. That is something that you all already talked about, and Professor Todorovic as well. Integral building design is a sustainable design, and it should be implemented in practice on a larger scale. I mean, this is good in theory, but it's not realistic so much in practice. It incorporates the balance of materials, energy, emissions, wastewater, waste or rubbish, and its disposal of recycling costs and life cycle into the building design, construction, and exploitation process. Basically, the use of energy piles is practical. I mean, that's a no-brainer. It's economical, it is good, and it should be used as an innovative technology. But the use of energy piles is practical because it integrates the system's structure bearing and temperature supply and regulation functions. Due to its complexity, compared to regular piles, a better knowledge of the application of this technology is necessary. But like you saw in the first example, it can be used on the piles that were designed already as regular piles. The use of energy piles involves the application of clean energy from renewable energy sources, which makes the application of this technology environmentally friendly and responsible to our planet, the ecosystem, and healthy civilizational and social development. Energy piles provide, as I already mentioned, non-polluting, sustainable energy, and they offer a reduction of fossil energy demand and CO2 emissions, which you were able to see on that chart from the authors of the United Kingdom. The use of geothermal energy as a clean and renewable energy source from pile foundation system is in continuous increase since their use began, which is shown already. And it would be very beneficial and socially responsible to continue with the use of energy piles and ground source heat pump systems technology and to find a way to achieve even greater and more practical implementation and integration worldwide, especially, like I mentioned already, in developing countries in order to use its full potential because of the environmental and economic justification that this technology provides. So here are the references. And I would like to thank you all for your time and attention.